When Niels Bohr considered a model for the arrangement of electrons in the atom, he knew that it must explain two key properties of atomic emission spectra. Firstly, why are they line emission spectra as opposed to being continuous? Why are there only a few frequencies present in these spectra? And secondly, why does every element have a unique fingerprint emission line spectrum that can be used to identify elements? Prior to Bohr, based on classical physics, it was thought that electrons in the atom could occupy orbits around the nucleus of any radius, and therefore have any quantity of energy. Bohr, however, suggested that the energy of electrons in atoms was quantized. This means that only certain values of energy are possible, that electrons could not have any quantity of energy on a continuous scale, but rather can only have specific discrete values in a given atom. Temperature, for example, is not a quantized variable. It can have any value above minus 273 degrees Celsius. If temperature was quantized, it would be like saying, for example, that only 4 temperatures are possible in the room you were in right now. 10 degrees, 30 degrees, 50 degrees, and 80 degrees Celsius, for example. The temperature can never be any other value than these, and in changing from one temperature to another, it will jump instantly between them, never having a value in between. This is how Bohr proposed that electrons were arranged in the atom. They existed on different energy levels, but these energy levels were quantized, and if an electron occupied a particular energy level, it had to have the quantity of energy corresponding to that energy level exactly. Nothing else was possible, and in moving between these energy levels, electrons would need to instantly change their energies, either gaining or losing the difference in energy between the energy levels. Bohr thought of electrons as moving around the nucleus in fixed orbits like planets. Each of these orbits is an energy level, or a shell, represented by the letter n. N equals to 1 is the first energy level, and so on. Note that the concentric lines become increasingly closer as you move up through the higher energy levels. This represents that energy levels become increasingly closer in energy as you move up through them. You should always show this in any diagram that you draw in the exam. Energy levels, however, are more easily represented as horizontal lines rather than circles, but both types of diagrams represent the same thing: electrons moving around the nucleus and having a particular quantity of energy as determined by the energy level it occupies. We will represent the quantity of energy that electrons have when they occupy an energy level as E, E1, E2, and so on. A common analogy to represent the quantized energy of electrons in an atom is the potential energy of a book on a bookshelf. Each shelf is a different height from the ground, and as the height increases, so too does the potential energy of the book. But the quantities of energy the book can have is determined by the height of the shelf only. Nothing in between is possible. If a book is in between shelves, the book will simply fall to a lower shelf, losing energy as it does so, to assume the potential energy it has on the shelf that it falls to. In the case of the hydrogen atom, for example, there is only one electron. Electrons always occupy the lowest available energy level. This is known as their ground state. The ground state of the electron in a hydrogen atom is n equal to 1. Here the electron is closest to the nucleus and is at its most stable, since it has the lowest quantity of energy it can have in a hydrogen atom, occupying as it does the lowest energy level. An electron in its ground state can jump to higher energy levels, but of course it will need to gain energy to do this. This energy that can promote the electron to a higher energy level can come in the form of heat, such as from a Bunsen flame, as we see in flame tests, in the form of electricity, as in a discharge tube, or indeed from light, since light, as we said before, transfers energy. But how much energy does the electron need to gain? Well, to occupy the higher energy level, it would need to gain the difference in energy between the two energy levels. For example, in our diagram here, if it jumps to n equal to 2, it will need to gain the difference in energy between these two energy levels, E2 minus E1. An electron that is being promoted to a higher energy level by gaining energy is known as an excited electron. This is an unstable state, and an excited electron will immediately fall back to a lower energy level, losing the difference in energy between those energy levels, again, E2 minus E1. This energy that is lost is given off as a photon of light. And what frequency does this light have? Well, we could work that out using Planck's equation, where the difference in energy between the energy levels divided by Planck's constant will give us the frequency of the light given off. The key point is that light of a specific frequency is given off, and that frequency is determined by the difference in energy between the energy levels that the electron is falling between. and these will give us the lines in our emission spectrum. Before looking in more detail at electron transitions, let's first quickly revisit our continuous spectrum. We know that a continuous spectrum contains all frequencies of light in the visible range. This range goes from around 450 by 10 to the 12 Hz at the low frequency red end of the spectrum to 750 by 10 to the 12 Hz at the high frequency violet end. Beyond the lower end is low frequency infrared radiation, and beyond the higher end is high frequency ultraviolet radiation, neither of which we can see with our eyes. Don't forget that a low frequency means a long wavelength, and a high frequency means a short wavelength. Again, it is important to stress that the lines representing the energy levels are not evenly spaced, but rather become increasingly closer together as we move up through them. This is important as it means that there is a much bigger difference in energy between n equal to 1 and n equal to 2 than there is between n equal to 4 and n equal to 5, for example. This in turn will mean that which energy level an electron falls to will be a much more important factor than which energy level it falls from in determining the amount of energy released and the frequency of light given off. It just so happens that in hydrogen, when an electron falls to n equal to 2, the frequency of energy given off will always be in the visible range. It doesn't matter which energy level it falls from. These lines are known as the Balmer series. You don't have to remember the names of these series. An electron falling to n equal to 1 will give off significantly more energy because of the large difference between n equal to 1 and n equal to 2. And so these lines on emission spectra are in the higher energy ultraviolet range and invisible to our eyes. Finally, an electron falling to n equal to 3 will give off less energy, and these lines will be in the lower energy infrared range and are again invisible to our eyes. Let's take a closer look at transitions to n equal to 2 in the hydrogen atom. If an electron falls from n equal to 3 to n equal to 2, this quantity of energy lost corresponds to a red color in the visible spectrum, as determined by Planck's equation shown here. An electron falling from n equal to 4 to n equal to 2 will give off light of a higher frequency corresponding to a green line in the visible range. An electron falling from n equal to 5 to n equal to 2 will give off light of a higher frequency again, corresponding to a dark blue line in the visible range. Note also how this line is much closer to the green line than the green line was to the red line. This phenomenon, as we said before, is called convergence, and we can see here it is because of the decreasing energy differences as we move up through the shells. Finally, an electron falling from n equal to 5 to n equal to 2 will give off light of a frequency corresponding to violet in the visible range, and this line again displays convergence. In this way, we see how the energy levels and their arrangements in the atom affect the distribution and colors of the lines in the emission spectra of atoms. Since in any spectral series, the frequency of lines are determined by the energy level the electrons are falling to, the lines will become closer and closer as the higher energy levels the electrons are falling from become closer and closer in energy, until eventually the lines will blend into each other such that they cannot be any longer distinguished from each other as individual lines. This point is known as the convergence limit. It is considered to happen at a point known as n equal to infinity, where an electron has been excited by so much energy that it is no longer considered to be held by the nucleus, and so has effectively been lost by the atom. This, of course, is the ionization energy, and you can be asked to determine the ionization energy from the frequency of the convergence limit. Consider this question, for example. Spectral lines converge at 9.1 by 10 to the minus 8 meters in the emission spectrum of the hydrogen atom. Find the first ionization energy of hydrogen in kilojoules per mole. Since we are given the wavelength, we will first find the frequency of the wave using the equation c is equal to f times lambda, where c is the speed of light, 3 by 10 to the power of 8 meters per second. This gives a frequency of 3.3 by 10 to the 15 hertz. We can now use this to find the amount of energy in a photon of this frequency by using Planck's equation. Multiplying by Planck's constant gives us an energy of 2.19 by 10 to the minus 18 joules. Of course, this is the amount of energy released by a single electron when it falls from n equals to infinity. But of course, the definition of first ionization energy is the amount of energy required to remove 1 mole of electrons, and so we must multiply this number by Avogadro's number to find the amount of energy for 1 mole of electrons. We can then divide this by 1000 to convert from joules to mole to kilojoules per mole. Our unit of energy on top is getting bigger by a factor of 1,000, so our number must get smaller by a factor of 1,000. Before we look at some typical IB-style questions, it is worth asking why all elements have unique fingerprint spectra. This is simply because, since each element has a different number of protons in the nucleus, they will in turn have a different and unique distribution of energy levels, since the negatively charged electrons will be affected by the amount of positive charge in the nucleus pulling on them. This will mean that different electron transitions are possible from one element to the next, which give off different colored lines in their emission spectra. Hence, we can identify elements accurately in tiny amounts by examining their spectra. Typical questions in paper 1 on this material tend to focus in on electron transitions in the hydrogen atom. Here in this question, for example, we are asked to identify which electron transition corresponds to a red line in the hydrogen emission spectrum. C, of course, is not an option since here energy is being absorbed. A is not an option because, of course, here the electron is falling to n equals to 1, and so this frequency will fall in the ultraviolet range. The answer can only be B or D then, since both of these fall to n equal to 2, which gives us lines in the visible range. But which one? Well, the red line will be of the lowest frequency, since it is closest to the infrared range, and so this will correspond to the lowest quantity of energy being lost, which will be B, since D is falling from a higher energy level, releasing more energy, and therefore a higher frequency photon. In this question, we are asked to identify which line would correspond to the ionization of hydrogen. All of our electron transitions are absorbing energy, but of course first ionization energy corresponds to the quantity of energy needed to move the most loosely bound electron to n equals to infinity. Since this is a hydrogen atom, the only electron will be in n equal to 1, and so our arrow must go from n equals to 1 to n equals to infinity, and so the correct answer is C. In this question, we are asked to identify the electron transition which emits radiation with the longest wavelength. Of course, C is not an option, since in this transition, energy is being absorbed, not emitted. The longest wavelength will mean, of course, the lowest frequency, which will correspond with the lowest energy. Since A falls to the lowest energy level, it will release the most energy, so this is not an option. Comparing B and D, we can see that B releases less energy since it falls from a lower energy level, and so this will be the line with the longest wavelength. If you'd like to practice some more of these Paper 1 style questions in a free quiz, follow the link in the description below. If you'd like to see more of this content specifically designed for IB chemistry, please consider liking and subscribing, and make sure to click the bell icon so you never miss a new video. Thanks for watching.